Ever wondered how AI systems like GPT-4 or BERT understand language so deeply? The answer lies in a revolutionary architecture called the transformer. Today, we're diving into the technical heart of transformers, how they process information, why they outperformed older models, and what makes them the backbone of modern AI. If you've ever wanted to grasp the mechanics behind language models, this is the video for you. Before transformers, recurrent neural networks (RNNs) and convolutional neural networks (CNNs) dominated sequence modeling. But they had critical flaws. RNNs struggled with long-range dependencies due to vanishing gradients, while CNNs relied on fixed receptive fields, limiting their ability to capture global context. Imagine trying to understand a paragraph where each word's meaning depends on something mentioned 5 sentences back. Traditional models floundered here. This gap set the stage for a breakthrough. Enter the transformer, introduced in 2017 by Google researchers. The key innovation: replacing recurrence with self-attention mechanisms. Let's break this down. At its core, a transformer consists of encoder and decoder stacks. The encoder processes input tokens, while the decoder generates output. But the real magic happens in the self-attention layer. Self-attention allows each token in a sequence to dynamically attend to every other token. Here is how it works. For a given token, the model computes 3 vectors: queries, keys, and values. The attention score between a query and a key is calculated using a dot product, scaled by the square root of the key dimension. This score determines how much focus a token should have on others. The final output is a weighted sum of the values, where weights are the attention scores. This enables the model to capture long-range dependencies and contextual relationships with unprecedented efficiency. But wait, how does the model know the order of tokens? Enter positional encoding. Unlike RNNs, which process sequences sequentially, transformers process all tokens at once. To preserve order, positional encodings, learned or fixed sine cosine functions, are added to token embeddings. This allows the model to infer positional relationships while enabling full parallelization, a game changer for training speed. To further enhance performance, transformers use multi-head attention. Instead of a single attention mechanism, the model splits the query, key, and value vectors into multiple heads, each capturing different aspects of the data. For example, one head might focus on syntax, another on semantics. These outputs are concatenated and linearly transformed. Between attention layers, feed-forward networks apply nonlinear transformations, ensuring the model can learn complex patterns. Training begins with pre-training on vast corpora, where the model learns general language patterns through tasks like masked language modeling. During this phase, 15% of tokens are randomly masked, and the model predicts them based on context. After pre-training, the model is fine-tuned on specific tasks, like classification or translation, using task-specific data. This two-step process allows transformers to generalize across domains while adapting to niche applications. The transformer's impact is staggering. It's powered everything from chatbots to code generation tools. But the research hasn't stopped there. Models like BERT, RoBERT, and T5 have refined the architecture with innovations like bidirectional training, dynamic masking, and task-specific adaptations. Meanwhile, vision transformers, VTS, have redefined computer vision by treating images as sequences of patches. Transformers aren't just a technical achievement, they're a paradigm shift. By decoupling sequence processing from recurrence, they've unlocked new frontiers in AI. As research continues, we're seeing even more efficient variants, like sparse attention mechanisms and quantized models, making this technology accessible at scale. Whether you're a researcher, developer, or curious learner, understanding transformers is your gateway to the future of AI. Thanks for watching. Now go explore the papers, experiment with models, and see what you can build. Want to dive deeper? Check the description for links to the original transformer paper, Hugging Face implementations, and further reading. Like this video if you're as fascinated by AI as we are, and subscribe for more deep dives into cutting-edge research.